We are doing section 3.1 derivatives. When I made this video, my mic was turned off, so I'm going to try to add everything after, trying to figure out what's going on in the video. So in the last section, we learned average rate of change, and the slope of the secant line from P to Q there gave us the average rate of change for a function. So over a period of time, what's the average rate of change, which is the change in y over change in x. And then last chapter, we also related that to your velocity. So over a long period of time, what was your velocity? And then we introduced the idea of what is your velocity at a particular point, at one point. I believe we looked at the slope of the tangent line. So that red line gave you the velocity at an instant. At that point Q, what's your velocity? And what's kind of hard about that is how do you find a slope at a specific point? Because normally it's f of b minus f of a or b minus a or rise over run. But when you only have one point Q and you're trying to find the slope at that point, how do you do a rise over run when you only have one point? And that's where calculus comes in. With limits and calculus, you're able to do things you weren't able to do before, and that's why this is a calculus topic. So again, I'm trying to add the audio later, and I'm not sure what I'm talking about right there. So we are going to, I'm just saying this chapter is really important. This section is a foundation for your next 2 months of your life in this class. So make sure you are just absorbing all this, understanding all this, and we're going to figure out how to find the slope at one specific point at Q instead of an average rate of change, and it'll be called the instantaneous rate of change. And I'm not sure what I did originally, but I'm waiting for the video to switch. I'm probably babbling. I don't know what I was babbling about. Yeah, I don't know. Oh, I know what I'm talking about now. Okay. If you take that point P and slowly move it to Q, yeah, look at that. As you move it to Q, you will notice the slope of that secant line gets really, really close to the slope of the tangent line there. In fact, as P gets uber close to Q, it's the same thing. And so that's how we're going to find the slope of that tangent line. We're going to take the slope of that secant line, and we're going to see what happens in the limit as the distance from Q to P, that x distance, approaches 0 and gets smaller and smaller and smaller. So conceptually, this is what's happening. You need to understand the limit gives you the slope of the tangent line. That's why we spent the whole chapter on finding limits and understanding limits, is to lead to derivatives, which is one of the major topics of calculus. Basically, you do derivatives and antiderivatives and a lot of applications of that. So hopefully you see that. I'm not sure what's happening in the video. I'm sure it was awesome, whatever I was talking about. But I should be switching to an actual example. So we're going to do, show you how to do this. We're going to give you a definition, and we're going to give you a method to finding that. Looks like I'm talking about the rise over run is the slope of that secant line. That's the run I'm talking about. So again, look, as the distance, x distance from P to Q gets smaller and smaller, the slope of the secant line becomes the slope of the tangent line. It approaches it, and in the limit, it becomes it. Okay, so here we go. This is where I'm going to show you where the formula comes from. So we have the same graph. The function is x squared. We have the secant graph labeled, the tangent graph labeled, and we have the point A and the point X. And the slope of the secant line is, and we did this in the last video, so it's just a reminder. So when x is a, to find the y coordinate there, you just follow it up and you move over, and the y coordinate there would be f of a. It's the function at a. And so we'll do the same thing with x. The y-coordinate at that point would be the function at x, f of x. So the length of the rise, you subtract the y-coordinates. So that's just going to be f of x minus f of a. And that's what we talked about. How do you find the distance between 2 points? You just subtract them. So the rise in this case will be f of x minus f of a. The run, you do the same thing. How far apart is x and a? You subtract it. X minus a is the run. So the slope of the secant line is just going to be the rise over the run. There's a rise, there's a run. We divide those, and that's the slope of that brown secant line. So let me go ahead and write that down for you. So here's the rise over the run, x minus a, and that is the slope of the secant line. Now, what did we do in that previous screen we had? We let x approach a, and we're going to see that. Oh, also, in the last section, we called this the average rate of change. You have to know the slope of the secant line is also the average rate of change. And we said f of b minus f of a over b minus a. This is f of x minus f of a over x minus a. The variables don't matter. I can call it a and b, a and x. You need to get comfortable with different ones. Now, how do you find the slope of that tangent line? In that last example, we let x get closer and closer to a. And in the limit, as that happened, the slope of the secant line approached the slope of the tangent line there. And so, remember in this video, we're going to show you, as the distance from P to Q decreases, as the x-coordinate at P approaches the x-coordinate of Q, you're going to see the slope of that brown line approaches the slope of the red line, and in that limit, you find the slope of that red line, which is the tangent line. So that concept needs to be in your head and you understand what's going on. So to find the slope of the tangent line, we have to do a limit. So let me write this down. I'll do it in red since the tangent line is red. The slope of the tangent line is, we do the limit as x approaches a. So remember, we have to have that point x get closer to a of that slope. So x is approaching a, so I'm going to write this down. The limit as x approaches a of that secant line. We're taking the slope of that secant line. That is how to find the slope of the tangent line. So conceptually, you should see what's going on. You're finding the slope at point A. That's where the tangent line is, at A. So hopefully you are visualizing, and that is making sense. If you know the equation of the secant line, you just take the limit as that x point approaches the A point. And that gives you the tangent line at A. And in the book, this formula, I believe, is called Formula 1. When the homework asks you use the Formula 1, it's talking about this one. We're actually going to have a second formula to find the slope of the tangent line. We'll get to that, but I want to do some examples for you of how you use this formula. And we're going to do it in general and at a specific point. But this is huge. There's two formulas. You have to know this and not just memorize it. You need to memorize it, but visually, you should see what that is. The f of x minus f of a is the rise. The x minus a is the run. Why do you take the limit as x approaches a? Because as x approaches a, that secant line approaches the tangent line. All that stuff must be like in your brain, second nature. And so don't just memorize and move on. Please understand what's happening in this problem. So now we're going to look at the function x squared. And so we are going to, example, we're going to find the slope of the tangent line. And we're going to do it for f of x equals x squared. That's the function we just drew. And we have to do it at a point where just x equals a. And that's the point we did in our example. As x approaches a, you find the slope of the tangent line at the point A. It's at that point you're finding it because x is approaching A. So if we want to find it at A, we use that exact definition that we just gave you. So the slope of the tangent line is going to be the limit as x approaches A of f of x minus f of A over x minus A. And then we plug, well, f of x is x squared. That's easy. But f of A, we plug A in for x, and that's going to get us a squared. So we write the next line. F of x is going to be the x squared, so I put the x squared. I put a in for the x for the second one, and I'm going to get a squared. And then the bottom is going to stay the same. And this is where last chapter comes into play. If I let x approach a, I'm going to get a squared minus a squared on top, which is 0. A minus a on the bottom, which is 0. That's 0 over 0. That's indeterminate. And what did we do last chapter? You need to know this. You factor and cancel. That's what we did last chapter. The top is difference of two squares, so it's x minus a, x plus a. The bottom stays the same, and nice. X minus a's cancel. Plug in a, we got to answer a plus a. And so we have found that the slope of the tangent line at a is 2a. And so here's what's kind of cool. You can plug in any value of a, and you're going to notice the slope changes depending on where you are on the graph. At different points on the graph, you're going to have different slopes. And so you can pick any value of x, which we call a, and plug it in, and you can find the slope anywhere. I'm not sure why I went back to that. Oh, okay. So I'm emphasizing here, at that point, it's a steep slope. If you move farther back, it's not as steep. You move farther left, and it's almost the slope is 0. So depending on your x-coordinate, you're going to have different slopes of tangent lines. So x3, x2, x1. x1 is the smallest, x3 is the largest. So that formula there, whatever a you choose, you can find the slope at any point on the graph. Just plug in an x value, a number there. So now we're going to do the same thing, but instead of at a, we're going to find the slope at a specific point, not just a general point a, but we're going to find the slope at a specific point. And it's the same formula, it's just a little bit different. You have a number instead of a variable. Some of you might like this better because you like numbers better than variables. But in the previous one, a was actually a constant, a specific point. But in this case, our a will get an actual value. So at point A, when x approaches A, we find the slope at A. So A is the point of tangency that we're looking at. So in this next example, we're going to have the slope at the particular point 1. 1 is our A, so x is going to approach 1. And then we do our same formula. We're going to do our f of x minus f of A, which is 1, over x minus a, and then you just plug in the values. So we still have the limit as x approaches 1, but now f of x is still x squared, but we plug in 1 for x, for f of 1, and we see the limit's going to be 0 over 0, which is indeterminate. So if that's the case, we have to do the factoring and canceling like we did last chapter. And the top is the difference of two squares. Hopefully, if you aren't good at that, you're starting to see that. So the top is going to become x minus 1, x plus 1. And you can re-multiply that to double check. The x minus 1s will cancel. Plug in 1, the slope is 2. So when x is 1, the slope of the tangent line will be 2. And what's nice, if you look at the previous problem, you could have plugged in 1 for a, because that's the point of tangency, and you would have got a slope of 2 real quickly. So it's nice, the top formula, the first one we did, you can use it to find the slope anywhere on the graph, any a. The second one that we did, which you might like better, only tells you the slope at one point. If you want to find the slope somewhere else, you're going to have to do it all over again. So the first example is actually a little more versatile. You can find the slope at many different points, not just one point. So it's a more general way of doing it. So remember, what does that answer tell us? That is the slope of the tangent line drawn at 1 on the graph of x squared. So now we're going to look at another formula. It's another one. You have to know both of these. Make sure they both make sense. We have the slope of the secant line. It's still x squared. And the same concept now, except we're starting at x, and the distance between that and our point on the right is h. We're defining that as h. So instead of the point on the right being a, it's going to be x plus h, because you're moving over h. So that's the only difference. So instead of a, you're going to have x plus h. The x coordinate there is f of x. The y coordinate. And how do you find the y coordinate? You plug in x plus h, you get f of x plus h. So we're doing the exact same thing. So the rise of our secant line, we just subtract the values. So the top value is f of x plus h. The bottom is f of x, so we just subtract that. This is exactly what we did in the previous one, except our variables on our x coordinates are slightly different. And then the run is just h. We don't have to subtract. You can. X plus h minus x is h, but we've already defined that as h, so we're good there. So we are going to do the same thing. We want to let the point on the right approach x. So we're going to take the limit. So the slope of the tangent line, I'll do in red because the tangent line is red. It's going to be a limit again. And at the point on the right approaches the point on the left, h is approaching 0, the distance h. So instead of saying x plus h is approaching x, we're just going to say the limit as h approaches 0, because h is the distance between those 2 points, x coordinate. And then we do the rise on top, and then we're going to do the run on the bottom. So the rise will be f of x plus h minus f of x, and the run is h, so we write that as our slope of our secant line. So on top, f of x plus h minus f of x, on the bottom we're going to have our h. That is our formula. This is going to be the second formula that you have to know, you have to understand. You should be able to relate to the picture. Don't just memorize. Make sure it's sinking in. This is so foundational to everything you're going to do in the next couple of chapters and on. So please, please make this sink in. Now, just a reminder, the secant line, we've done that formula, also known as the average rate of change. In this case, will be the rise of a run only. But if you take the limit of that, now you have the slope of the tangent line. And this is formula 2 the book refers to. So when your homework says use the second formula for slope of tangent line, you will use this one. And so I'm now going to do an example of using this formula. And I'm going to do the same problem we did before. So I'm going to go ahead and lasso it, and then I will cut it out or copy it out, and I will paste it down below. So let me grab my lasso tool. Let me copy that and scroll down. Let me paste it right in here. And I gotta scoot it over. We will work this out. So now we're using the second slope of the tangent formula. Let me write this down. So we're going to use that formula 2 sitting right there. So we're finding the slope at x equals a. So now x here is actually a in this formula because we want it at a. So when we write this limit thing, the x's will become a's. And actually you could leave them x's and it will be the slope at x. It's just a variable, and technically it really doesn't matter what I call it. So later on we'll probably just leave it as x and not put it as a. So we're going to replace the a plus h in for x and then the a in for x to get our two formulas. So on top we replace x squared with a plus h, so a plus h squared, and then the second one we just put in the a in for x because it's a function at a, and so that's just going to get us x squared, so we'll do that. The bottom is just h. Now when we take this limit again, you're going to get 0 over 0, which is indeterminate. Sound familiar? So we need to factor and cancel. Now, for those of you who are quick and you can see it, there's a quick way to factor the top. That is a difference of two squares. So if you see that, you can just do the first minus the second and the first plus the second. And I'll go ahead and do this on the right here for those of you who see it, but then I'll do it the long way for those who don't. So it's the first minus the second plus, or times the first plus the second. That is the factoring of the top. But if you don't see that, we're just going to have to multiply out the top. So the a plus h squared, make sure that you're multiplying a binomial. That a plus h squared, write it out, a plus h times a plus h, distribute everything. You end up with a squared plus 2ah plus h squared. Don't forget the 2ah, and then the minus a squared still there, over h. Nice, look at this. The a squared and the a squared cancel. That is so beautiful. So those will disappear, and we will have left the limit as h approaches 0 of 2ah plus h squared over h. But sadly, you plug in 0 for h again, you get 0 over 0. So again, we need to factor and cancel. So we'll notice that both terms on top have a common factor of h. Whenever there's a common factor, that's the first thing you should do. We're going to take the h out, and we're left with 2a plus h, and the h's cancel, just like last chapter. And now we let h approach 0, and you get 2a for your final answer. Now, that is the exact same answer as we got above when we did the other formula, Formula 1. And they better come out the same because they're the same thing but just written differently and attacked slightly differently. So that is the slope of the tangent line at any point A. Just you can replace any value of x for A and you can find the slope at that point. So you should know all of this is leading to the idea. Oh, I was going back to the first one, showing you the first factoring was exactly the same. I forgot. So that's what I was doing there. So if you saw that as a difference of two squares, you could have factored it a lot more quickly. So this is the derivative. The slope of the tangent line is the derivative. So we're going to give you a definition. So now we just had formulas how to find the slope of a tangent line. But now formally we're defining the derivative. That little apostrophe on the f, that is the notation for the derivative of f. The derivative of f of x, by definition, is this limit that we just found, formula number 2, the slope of the tangent line. So I'll write that down. So some connections need to be in your head. When you hear derivative, you have to understand what that is actually telling you. What is the derivative? What is it? And so it is the slope of the tangent line. That needs to be in your head. You should see a tangent line to a graph and you think the slope of that line is the derivative. Because if you understand that formula, that's the slope of the secant line, f of b minus f over b minus a. As h approaches 0, that is the slope of the tangent line. So f prime of x is the slope of the tangent line, needs to be ingrained in your brain, not just memorized, but visually you should see that. If you don't know what a tangent line is, you need to know, or else you'll be very confused and not be understanding a lot of things this chapter. So first of all, one of the things, f prime of x is the slope of the tangent line. And now if you remember, in the last section we did, the f of b minus f of a or b minus a was the average rate of change. And we talked about how do you know your velocity at a specific point, at an instant? That was the slope of the tangent line. So here's the other thing. The derivative is the instantaneous rate of change. It's not over an average. It's at a specific point, it's your rate of change. So that's the next thing that you have to know. The derivative is also known as the instantaneous rate of change. It's just assumed that you will know that. That should be known not just by memorizing, it's understanding. As h approaches 0, you're finding the slope at an instant. And the slope is a rate of change. So if you are having trouble learning these, make some flashcards, draw some pictures. You gotta let these sink in. What is a derivative? How do you find the derivative? And that's the definition of the derivative. That definition is the limit as h approaches 0 of fx plus h minus f of x over h. So that is the definition. Now, there are a lot of notations how we describe derivatives, and you have to know that. So f prime of x, you have to know means derivative. dy over dx is another way of saying derivative. Now remember remember delta? Delta means change in y, and delta x is change in x. Well, d is kind of like the same idea of delta, but the difference, the delta is a big change in y. The d is what happens in the limit as that distance approaches 0. The limit as h approaches 0 or x approaches a, that distance approaches 0. So when you use that little d, it's implying an infinitesimally small change in y. And the dx, the infinitesimally small change in x. So therefore, instead of being an average rate of change, the dy dx is an instantaneous rate of change. It's implying an infinitesimally small change in y and x. Now, another way we write this, we do the d dx, but instead of putting the y there, we put f of x. So that's the way the derivative of the function f of x can be written that way, where the top is a change in f, which is y, and the bottom is the change in x. So recognize that as another way of saying the derivative of f of x. And then y prime of x. So instead of f, it's y prime. It's a change in y or a change in x. And y prime without the x is also a common notation for the derivative. Now, what I don't like about the last one, you don't know your independent variable. The rest of them, you see the x is there. You know the y is the dependent and the x is the independent. On that last one, you do not know what the independent variable is. And that comes into play when we start doing related rates. And the variables aren't always y and x, and you need to be okay with that. Now we also find we need notation. The first set we have there is the general derivative. But what if you want a derivative at a specific point on the graph? So there's notation for that. So we will do an example at a specific point 1. What's the derivative at 1? Well, clearly f prime at 1. But how do you do that on the next one? dy dx. How do you say find the derivative at 1? Well, you draw a line to the right and you just put x equals 1. So that's how you find, in that notation, the derivative at a specific point. And then I did the same thing twice. That was kind of weird. I don't know why I did that. I probably meant to put f of x. And then the last one, y prime at that should be a 1. I'll fix that. It's a lot easier after the fact. So that's just a notation of how to write the derivative at a specific point. You should know that because you're going to be seeing that. So the bottom one at a specific point, and the top is just a general. All right. I know this video is pretty long, not as long as some of the other ones. I think it's 40-something minutes. But there's one more really important thing, and it's the application of derivatives. You will be doing this the rest of the year. This is a common AP question. This is a common thing that you do in the AP class. And it involves equations of lines. And what am I doing? To find, I think it's going to be the equation of tangent line. Oh, I haven't done that example yet? Oh, I know what I'm doing. Okay, I'm getting ahead of myself. We're going to do a different function. We've only done x squared. Now we're going to do x squared minus 2x. And this gets kind of, you might think, oh, we already did x squared. This is not a big deal. This kind of gets messy. And it can get pretty messy really fast. You'll see on Monday when we do more of these, it gets really messy. So we're doing the second definition. The limit as h approaches 0. And then it's going to be f of x plus h minus f of x over h. So now we have to plug that x plus h into both those x's in our f function. So it's going to get a lot messier. So I plug that in for both x's. And so I'm going to get x plus h squared minus 2, and then the x plus h in for the second one. That's the first function, minus the second function is just the actual equation, just f of x. So I need to put that in brackets or parentheses because I'm subtracting the whole thing, or you'll mess up if you don't do that. Now I square the x plus h, and again, don't forget the middle term. You have to make sure you square binomials correctly. Write it out the long way if you need to. X plus h times x plus h, then do it. Don't forget to distribute the negative 2 to both of those. So it's minus 2x minus 2h. You have to distribute that. And then I have to distribute the negative to the last 2. That's why don't forget the brackets or parentheses around that. Nice things happen again. Do you see the x squared and the minus x squared? Bam. Do you see the minus 2x and the plus 2x? Nice. Bam. Beautiful things happen when we do this right. And then we write what's left. So on top, we're going to be left with the 2xh plus h squared minus 2h. And the bottom, we have an h. And sadly, when we plug in h, we get 0 over 0. Does that sound familiar? Indeterminate? So we're going to factor and cancel. And fortunately, the top, they all have a common factor. If you look, they all have an h. So we're going to take that h out. And that's going to be awesome because you're going to see the h's are now going to cancel. Beautiful. Now we let h approach 0. And we're going to be left with 2x minus 2. That is the derivative for x squared minus 2x. Awesome. So that, it gets ugly. You're going to see. Some functions are easy to do derivatives. Others, ooh, you're going to be hating me. But I'll be nice to you guys. I just want you to make sure you understand the basic concept of what the derivative tells you, how to find it. And these examples that you practice are just so you understand what's going on. And so I'm not going to give you like an x to the 4th power because that would be ugly, or an x cubed. I'll keep it simple. But you are going to get maybe some square roots and some fractions. So we'll work. There's not going to be a lot of problems, but there's going to be some not so pretty problems. All right, we're going to have a part B to the problem we just did. This is what I was talking about, the equation of the tangent line. This is what you're going to find this so many times this year. I'm not lying. You might be asked 100 times this year to find the equation of a tangent line. And I might not be lying. I might be, but it's a lot. And this is so basic. We're going to find it at a specific point at 2. If I didn't give you a point, you really couldn't find the equation of the tangent line. So our equation is x squared minus 2x. So I'm going to graph this for you so you kind of have a picture of what's going on. It has x-intercepts of 0 and 2, and it's a parabola that opens up. So if you factor that and set equal to 0, you'll see the zeros are 0 and 2. And you just draw a parabola through those points. And then the tangent line at 2, I'm going to do it in red. It's almost like I'm slow-mo. What's going on? Pick the red, Yoshida. Pick the red. I don't know what I'm doing. Come on. Okay. So there's 2, and there's a tangent line through 2. You want to find the equation of that line. You need to know the point-slope form of a line equation. Plain and simple. I will quiz you on this. It needs to be something where it's instantaneous. You just have to know this. It actually comes from a slope formula. And I don't mention that. I probably should have mentioned it. But here is the equation of a line with the slope of m. So you need the slope with slope m and through a point, and that point is going to be x1, y1. So to find the equation of a line, you need a point and a slope. And the equation will be this. And you have to know this. This is what you have to memorize. It's going to be y minus y1 equals mx minus x1. You just got to know that. Now, if you move the x minus x1 to the left, that's the slope formula. Difference in y's or difference of x's. You have to know that. That is something that you're going to be using all year long. So I'm going to quiz you all year long. You got to know that. So you need to know the slope and a point. So in our example, do we have the slope and the point? Well, we're given the x-coordinate of the point of tangency, right? It says the tangent at x equals 2, right? So we know at 2, so we know the x1 of the x1, y1. So that's going to be 2 comma something. How do I find the y-coordinate of that point of tangency? Well, I just plug the 2 into f of x. It's f of 2. And if I work that out, it comes out to be 0. How nice. How nice. So now I have x1, y1. How do I find the slope of that red line? How do I find the slope? Duh. The whole purpose of this lesson was finding the slope of a tangent line. The slope of the tangent line is the what? Derivative, right? And how do I know the derivative of that function? Well, we just did it on our previous problem. The derivative is 2x minus 2. So if I want to find the derivative at the point 2, because that's where they're asking us, I have to find f prime at 2. So the slope of the tangent line is f prime at 2, and we found that above. So that's just going to be 2 times 2 minus 2. And that will be the slope at that particular point, which comes out to be 2. So I know the slope, I know the point, I am done. I just plug it into my formula. I plug the 2 for the x1, the 0 for the y1, and the other 2 for m, and I have found the equation of the tangent line. Make sure you know how to do that. Please don't delay. You're going to be asked to do that a lot this year. We have something called a tangent line approximation in BC. You have Euler's. You have so many times where you're going to just use that. It's such a common thing. Please take the time to make this make sense. So I plug 2 for the slope. x1 is the 2. y1 is a 0. Bam, there it is. That is the equation of the tangent line of y equals x squared minus 2x at the point 2. And that's it for the section. Please absorb this, make sure it makes sense. This video is keep on going, it keeps going, and I'm not sure what I'm telling you. Oh, I think I'm pleading with you. Please make sure you don't fall behind. Make sure this all makes sense. Don't procrastinate. You need this foundation, all right? Have a great rest of your weekend. Bye.